Welcome to Module 8, where we connect agriculture, energy, and technology. Farming is one of the most energy-intensive systems in the world, powered by tractors, pumps, factories, and trucks. Even grocery stores rely on energy to keep food cold. Most of that energy still comes from fossil fuels, which is not sustainable. In this module, we'll examine how farms use energy, how technology is making systems smarter, and how waste can be turned into a resource. You'll see examples like solar-powered irrigation, drones that detect crop diseases, and digesters that convert manure into fuel. As we move through this lesson, keep one question in mind. How can science and innovation help us feed the world in a way that is sustainable for both people and the planet? We'll cover 3 quick points. First, energy. Most farms still rely on fossil fuels, but renewable sources, such as solar energy, are increasing in use, especially in California. We will identify energy sources, compare them, interpret trends, and evaluate the implications of using renewable energy instead in agriculture. Second, smart tools such as solar pumps, LED lights, and drones help save water, cut energy use, and reduce waste. We will describe irrigation tools to reduce waste, analyze the impact of alternatives in indoor agriculture, and explain how new technology can improve efficiency and reduce emissions. Third, farms are starting to close the loop, turning waste into power using digesters and utilizing solar energy to run chillers and irrigation systems. The big takeaway is that smart energy equals sustainable farming. Before we dive in, I want you to pause and just think about this question on the screen. How is energy shaping the future of farming? Take a moment and reflect on what comes to mind. No pressure, just your thoughts. What are some words and ideas you associate with that question? Majority of the energy comes from conventional energy sources, as seen in red. In 2009, the amount of energy consumed from renewable resources, as seen in green, was at 8%, and that number jumped incredibly to 30% by 2023. While the majority comes from conventional non-renewable sources, this increase shows significant promise towards the switch to renewable resources for energy. On farm operations, such as tillage, planting, irrigation, and harvesting, are heavily dependent on diesel. Tractors, combines, and irrigation pumps rely almost exclusively on internal combustion engines. Post-harvest operations, such as washing, packing, cooling, and processing, are mostly powered by electricity. These are typically more amenable to conversion into renewable energy sources, such as solar or wind. There are 6 main categories of renewable sources. Additionally, there are more types of renewable energy sources available for use, such as hydropower, wind, bioenergy, marine, and geothermal. Here is a table summarizing the benefits and limitations of conventional and renewable energy sources. Diesel is energy-dense but polluting. Combustion of diesel emits carbon dioxide, nitrogen monoxide, and particulate matter, which are major contributors to both climate change and air pollution. Electricity is cleaner only if its source is clean. If the grid is powered by coal or natural gas, switching from diesel to electric isn't necessarily greener. However, if paired with renewables, electricity becomes a powerful tool for decarbonization. Every food item carries an invisible energy signature, energy used to produce inputs, for example, fertilizers, run machinery, irrigate fields, transport goods, and maintain cold chains. A head of lettuce grown in a conventional system may require significantly more energy than one grown in a controlled environment that uses renewable energy and efficient logistics. What do you think uses more energy? A pound of beef or a pound of lentils? Why? Please take a moment to think about this. Keep in mind that if we want farming to be more sustainable, we have to plan for energy, not just plants and animals. And honestly, that's where all of you come in. You're the next generation of scientists, engineers, and decision makers, the ones who'll design smarter farms and food systems. So keep asking these kinds of questions. Here's a snapshot of global energy use in farming. Agriculture consumes about 18 to 30% of the world's energy. Diesel dominates field operations, from tractors to irrigation pumps, while electricity powers most post-harvest processing. Renewables like solar and bioenergy still make up less than 15%. The key issue is that diesel, a fossil fuel, is highly polluting. Electricity only becomes clean when it's paired with renewables. This picture shows us why energy transitions in farming are critical to climate solutions. This visual shows where greenhouse gases come from globally. More than 70% come from energy use, powering factories, buildings, transport, and more. Agriculture, forestry, and land use make up almost 20%, driven largely by livestock, manure, and deforestation. The point is clear. Energy is the main driver of emissions, but farming is also a major piece of the puzzle. If we want sustainable food systems, we need to address both energy use and agricultural practices. Let's take a quick snapshot of how farms use energy. Most people think of diesel first. It powers tractors and harvesters in the fields. However, farms also require electricity to operate equipment such as cold rooms and wash pack stations, which help keep food fresh and market ready. Now here's what's changing. More farms are using renewable energy like solar panels, wind turbines, and biogas. These systems help cut both costs and carbon emissions, especially in areas where electricity is expensive or unreliable. Why does this matter? Well, every tomato or jug of milk comes with an energy cost from planting to processing. And that's what we call embedded energy. And when we burn diesel, we add to greenhouse gas emissions. However, if farms switch to clean electricity, especially from renewable sources, we can reduce agriculture's impact on the climate. So here's something to think about. What kind of energy should we be using to grow food? And why does that choice matter for the planet? Let's zoom in on California. This state leads the country in on-farm solar energy. In fact, over 30% of the electricity on California farms comes from solar panels. That's a big shift toward cleaner farming. Many of these farms utilize a system called net metering, which means that if they generate more solar power than they use, they can send the excess energy back to the grid and earn a credit on their bills. Why is California ahead? Well, it has plenty of sun, strong state policies, and good support for clean energy. This is an excellent example of how geography, technology, and policy all come together to shape how we power our farms. So why is California such a leader in farm solar energy? First, sunshine. California gets strong sunlight almost year-round, especially in the Central Valley. That makes it ideal for solar panels. Second, state policies. California has some of the strongest clean energy laws and incentives in the country. Features like net metering, tax credits, and grants make it easier and more affordable for farms to install solar energy systems. And third, infrastructure. The state has a well-developed electric grid and permitting system, making it easier to get solar projects up and running. Additionally, electricity is expensive here, so saving energy is particularly important for farms. All of that adds up to make California a leader in solar farming. Let's talk about how net metering works. When a farm's solar panels make more energy than they use, the extra power goes back to the grid, and the farm gets a credit on its utility bill. It's like using the grid as a battery. This gives farms a reason to build larger solar systems. They can save money over time and potentially even recoup some of the costs associated with their production. Switching to solar also has significant environmental benefits. It reduces fossil fuel use, and solar panels last a long time with minimal maintenance. That said, installing solar isn't always easy. There are upfront costs, and smaller farms may have more trouble affording them. Still, in places like the Central Valley, more farmers are going solar, some even turning old cropland into solar fields. Today, over 115 California dairy farms produce enough solar power to run about 30,000 homes. The big picture here is about moving toward a more sustainable and self-sufficient future. At its core, California's shift to solar represents a move toward energy independence, where farms and communities generate a greater portion of their own power and rely less on fossil fuels. This is also a key strategy for climate resilience, as it helps reduce emissions and air pollution while saving money over time. However, there are still major hurdles, including high upfront costs and ensuring that all communities have equitable access to these systems. Overall, this transition is about reimagining how we power our lives in a way that is cleaner, smarter, and more reliable. All right, let's slow down and think about something we do all the time: eating. Imagine you're making a simple salad, maybe lettuce, cucumbers, and tomatoes from ingredients you got at the store. Now here's the challenge. How much energy was used before that salad hit your plate? Was it the tractor that grew the lettuce? The truck that delivered it? The cold room that kept it fresh? Take a minute and try to list at least 5 places where energy was used. Then turn to a partner and share what you came up with. Want to go a little deeper? Pick one item, a gallon of milk, a pound of beef, or a bag of spinach, and try to break down the energy used at every stage. Think about how it was grown. Did it need feed, fertilizer, water? How it was processed or packaged? How far it traveled and how it was stored? And how it stayed cold at the store. You're basically tracing the energy path from farm to fridge. Now let's wrap up this section with some review questions to answer. 1. What are the 2 main types of energy sources used in farming today? Give some examples. 2. Why is California a leader in using solar energy on farms? 3. What does embedded energy mean, and how does it apply to the food we eat? Please take some time to review and answer these questions. Some possible answers to the questions would be 1. Conventional, fossil fuels like diesel and coal, and renewable, like solar, wind, and bioenergy. 2. California contains an abundant amount of sunlight, strong state policies, and good infrastructure for clean energy. 3. Embedded energy would be defined as the total energy used to grow, process, and transport food. For example, lettuce needs energy for watering, harvesting, and shipping. Let's kick off Lesson B with a big question. How can technology help farmers do more with less? We all know about food, and we all know about tech, but have we really stopped to think? How do those two connect? How does innovation actually help us grow food more efficiently? In this lesson, we'll examine 3 technology categories that are transforming farming. Smart irrigation systems, controlled environment agriculture such as greenhouses, and precision field tools, including drones and robots. Each of these tools helps farmers use less water, energy, or chemicals, while also helping them grow more or adapt to climate challenges. So today's lesson is really about solving some of farming's oldest problems, but with new tools. And we'll see some real-world examples of how that's happening right now. Let's talk water. Did you know agriculture uses about 70% of the world's fresh water? That's huge, and it's why smarter irrigation really matters, especially in dry places like California's Central Valley. So here's the big question. If water is one of the most limited resources in farming, how can we use it more efficiently? That's where smart irrigation systems come in, especially something called VFDs or variable frequency drives. Think of them like dimmer switches for irrigation pumps. Instead of blasting water at full power all the time, these devices adjust the pump speed based on the crop's actual needs, using real-time data from soil moisture sensors. This prevents overwatering, saves energy, and avoids pressure damage to equipment. But access isn't always easy. As we proceed, consider this as well. What makes it challenging for small farmers to access this technology, and how can policies or subsidies help? Let's look at another powerful tool in smart irrigation: solar-powered pumps. Instead of relying on diesel or needing to be plugged into the grid, these systems use solar panels to pull energy directly from the sun. Here's how it works. The solar panels capture sunlight and convert it into electricity. That electricity is stored in a battery, and from there, it can power devices such as pumps and moisture sensors. This setup is super helpful in remote or off-grid areas, especially where electricity is expensive or unreliable. And, of course, it reduces fuel costs and helps lower greenhouse gas emissions as well. So, in a lot of ways, solar irrigation is helping farms become more independent and more sustainable. Now let's take a look at another major tool in smart irrigation: soil moisture sensors and how they work with IoT, that is, Internet of Things technology. These sensors are installed in the field and measure how much water is in the soil at different depths. The real-time data is then sent to apps or cloud platforms, allowing farmers to know exactly when and where to water. This isn't just about convenience. It helps prevent overwatering, saves energy, and makes the whole system more efficient. Smart irrigation uses just the amount of water crops need, no more, no less. Let's take a quick look at something really important: who gets access to smart farming tech. Not all farmers can afford high-tech irrigation systems. Many small farms don't have the money, the training, or the digital tools they need to use this stuff. And that's a real problem. This is where programs like California's Sweep come in. They help farmers pay for tools that save water and energy. There are also partnerships between public and private groups that work to make these tools more accessible. Our key takeaway is that smart tech is great, but it won't make farming sustainable unless everyone has a fair chance to utilize it. Now, you might hear terms like electrical conductivity, capacitance, or dielectric constants. These are science principles that help sensors detect moisture levels accurately. So, there is a significant overlap between physics and chemistry. Let's also zoom out and think big picture. When irrigation is more precise, plants grow better, fertilizer runoff decreases, and energy use drops. That's great for the environment and for a farmer's bottom line. So here's something to reflect on. What kind of crops or regions might benefit most from this kind of technology? And with climate change making weather less predictable, how might tools like this become even more critical in the next 10 or 20 years? Just as importantly, what happens if we rely too much on automated tech? Something to keep in mind. Smart irrigation represents a significant shift in how we think about farming. Historically, agriculture has been a resource-intensive endeavor, particularly in terms of water usage. However, as droughts become more frequent and water becomes more precious, we begin to require systems that are efficient, adaptive, and fair. Smart irrigation systems move us in that direction by helping farmers make data-informed decisions on when to water, how much to water, and how to align that with both crop needs and energy availability. Yet, this also raises questions about equity. Who has access to this technology? Who gets left behind? And how can policy help make these tools accessible to smaller or underserved farms? In essence, the big picture here is about rethinking agriculture as a system that can be resilient and thrive in a water-scarce world while supporting more farmers more fairly. Please look over these reflection questions and answer them. What kinds of crops or regions benefit most from smart irrigation? How might climate change make this technology more or less critical in the next 20 years? What are the risks of over-relying on automated or tech-based solutions in agriculture? What if we could farm anywhere in the Arctic, on a spaceship, or in the middle of a city with no soil and minimal water? That's the promise of controlled environment agriculture, also known as CEA, which uses science and technology to simulate ideal conditions for plant growth, independent of outdoor weather or soil quality. What is CEA? Controlled environment agriculture refers to a highly managed agricultural system where factors like light, temperature, humidity, carbon dioxide levels, and nutrient delivery are precisely controlled. CEA encompasses techniques such as indoor vertical farms, greenhouses with climate control, hydroponics, which is growing in nutrient-rich water, and aeroponics, which is growing in mist environments. Take a quick look at how light affects plant growth in CEA. So, plants don't just need light. They need the right kind of light. Specifically, they absorb light most efficiently at around 450 nanometers, which is blue light, and 660 nanometers, which is red light. That's because these wavelengths align with the peaks in chlorophyll absorption, which drives photosynthesis. Now, modern CEA systems use tunable LED lighting. What does that mean? It means we can program these lights to emit the exact colors plants need at different stages, much like a custom light recipe that helps increase yield and reduce wasted energy and heat. We also integrate this with adaptive HVAC systems to control temperature, humidity, and carbon dioxide, keeping the environment just right without overspending on energy. So, the big takeaway? In controlled environments, we can engineer light and climate to make food production more efficient and sustainable, even in urban settings or extreme environments, such as space. Let's dive into another key component of CEA: adaptive HVAC and climate control systems. These systems do more than just heat or cool a space. They're designed to regulate temperature and humidity in a way that supports photosynthesis while minimizing stress on the plants. Now, why does that matter? Well, temperature affects enzyme activity and transpiration rates, both of which are critical for healthy plant growth. However, there's a trade-off. HVAC systems consume electricity, so managing them efficiently is crucial to maintaining sustainable energy use. Another piece here is carbon dioxide enrichment. By increasing the level of carbon dioxide in the air, just up to a certain point, we can boost photosynthetic rates and help plants grow faster. In short, if we can optimize light, temperature, humidity, and carbon dioxide levels, we can maximize plant productivity while minimizing resource use. This is where LED lighting and HVAC systems work together to drive significant gains in energy efficiency and crop yield. All right, keep this in mind as we move forward. CEA isn't just about tech, it's about precision control for sustainable growth. Let's wrap up our section on controlled environment agriculture with a real-world application that's out of this world. Literally. Here's the big idea. NASA and researchers at UC Riverside are testing how to grow tomatoes and leafy greens in space. Yes, space. They use artificial photosynthesis and controlled environment agriculture systems to make this possible. These closed-loop systems recycle gases, such as carbon dioxide and oxygen, and manage nutrients efficiently, perfect for long-term space missions, like a trip to Mars. So what's the takeaway? These innovations aren't just for astronauts. They're teaching us how to build sustainable food systems on Earth, too, especially in places with drought, limited space, or urban populations. This shows us the power of science and engineering to rethink where and how food can be grown. Now, let's move into a fun, creative application of what we've learned. This is your activity corner on controlled environment agriculture. You've already learned about the science. Now it's time to apply it. You'll either work individually or in small teams to design a futuristic indoor farming system. You'll build a small LED-lit indoor farm for a school or community. Include crop selection, light spectrum choices, and even your energy budget. Think about closed-loop systems. How will you recycle carbon dioxide and nutrients? What kind of crops will you grow? Tomatoes? Mushrooms? Algae? And can you power it with solar or biogas? Finally, put together a short one-page proposal. Explain your scientific reasoning, your energy math, like calories per day, and reflect on possible challenges like cost or engineering limits. This is about more than farming. It's about solving global food problems with science, creativity, and teamwork. Let's get designing. Moving on to precision agriculture, a cutting-edge approach to farming that uses AI, drones, and smart robotics to optimize how we grow food. Here's the big idea. Precision tools help farmers reduce waste and increase efficiency. Drones scan fields with infrared cameras to create heat maps. These heat maps show where crops are healthy versus where they're stressed, often due to disease, pests, or a lack of water. AI apps can analyze these maps and even send early alerts if a disease outbreak is likely, allowing farmers to act quickly. Then there are spot spray robots. These only apply pesticide exactly where it's needed. That cuts chemical use by up to 70%, saving money and protecting the environment. Imagine you're building your own farm robot. What would you want it to do? How would it help a farmer work smarter, not harder? Overall, precision agriculture is about working smarter with data, treating plants individually instead of using a one-size-fits-all approach. Efficient, sustainable, and smarter farming powered by technology. Smart sprayers aren't just about automation. They're about precision and conservation. They can reduce airborne spray drift by up to 87%, resulting in less pesticide ending up where it shouldn't. Spray loss on the ground drops by as much as 93%, meaning more of the product actually reaches the plant. Overall, pesticide use is cut by more than 50%, saving money and reducing environmental harm. And here's the best part. They maintain the same level of pest control as traditional sprayers. Despite all the benefits, tech-based agriculture comes with real challenges. Let's take a closer look at one of the biggest barriers farmers face: high upfront costs. Now imagine you're a small farmer trying to modernize your operation. You've heard that sensors, drones, automated irrigation, and AI tools can boost yields and save water. But then you start pricing things out, and you realize just getting the materials is already out of reach. That's the core issue here. Many of the latest technologies require expensive acquisition costs. That is, the cost of buying the equipment in the first place. And for farmers with limited resources, little credit access, or no financial cushion, these costs aren't just high. They're a hard stop. Innovation thus becomes something only the well-capitalized can afford. Let's continue with a deeper look at another critical issue: data sharing and ownership. Now imagine you're a farmer using AI to help manage your crops. You're generating tons of valuable data on soil, water, yield, even pests. But what if you don't actually own that data? That's the core of the issue here. When tech companies control cloud platforms where farm data is stored, farmers can lose control over their own business decisions. As it says here, you do not own your data. That means your freedom of business decisions can land in someone else's hands. This raises serious questions. Who gets access to that data? Can it be sold? Used to adjust prices? Influence insurance rates? It's not just a tech issue, it's a power issue. We're also seeing how this plays out across the country. Check the map. Usage of precision ag tech varies a lot by state. That's a clue that tech adoption isn't equal, and that digital divide still exists between states, regions, and farm sizes. As we explore agricultural innovation, we must think critically about how to ensure ethical, fair, and farmer-centered data systems. And how do we balance innovation with privacy, autonomy, and justice in the field? With smart technologies like drones, sensors, and AI-guided sprayers, farms can now perform tasks more efficiently. But there's a catch. As machines take over manual labor, like spraying, harvesting, or even weeding, it means fewer jobs for human workers, especially in rural areas where farming is a major employer. This brings up a key question. How do we balance the benefits of efficiency with the very real risk of job loss? Now, let's think critically. Do these new tools replace tasks that a person could do? And more importantly, who gains and who loses when these tools are adopted? I want you to reflect on a piece of technology, say a smart sprayer or an automated harvester, and ask, what are the upfront costs? What kind of data does it require? And what types of jobs might disappear? And here's something to debate. Should there be a farmer's data bill of rights? What would that protect? Now let's transition into a real-world application with our case study analysis. In this activity, students will take a deep dive into an actual precision agriculture company to understand how these tools work beyond the classroom. The focus is on uncovering three key pieces: the technologies they use, their impact on sustainability, and any ethical or social implications tied to those technologies. Think of this as detective work. First, what tools does the company rely on? Are they using satellite imagery, AI-driven drones, soil moisture sensors, automated tractors, or machine learning yield models? How do these tools actually function on the ground? Next, ask, what is the sustainability impact? Are they reducing water use, cutting fertilizer waste, lowering emissions, improving soil health, or maybe helping farms adapt to climate stress? This is where students connect technology to environmental outcomes. And finally, here's the critical part. What are the ethical or social implications? Who benefits? Who might be left out? Are there issues around data privacy, cost barriers, labor changes, or unequal access between large and small farms? These questions push students to look beyond the tool itself and consider the people and systems affected by it. By analyzing a real company, students get to see how precision ag tech plays out in the real world: the good, the promising, and the complicated. This activity brings together everything we've explored: innovation, sustainability, ethics, and the broader social impacts of agricultural technology. Now let's wrap up this section with some review questions to answer. 1. How do smart irrigation tools like sensors and solar pumps help farmers save water and energy? 2. Why are LED lights and HVAC systems important in indoor farms? 3. What do drones and robots do on farms, and how do they help the environment? Please take some time to review and answer these questions. Some possible answers to the questions would be: 1. The smart irrigation tools would use data and solar power to give crops just the right amount of water, which cuts waste and saves money. 2. LED lights give the best kind of light for plant growth while using less energy. HVAC systems regulate the temperature and humidity to support optimal plant growth. 3. Drones check plant health, and robots spray only where needed, which reduces pesticide use and protects the soil and water. How can farms transform waste into something valuable? We're now exploring the concept of a closed-loop system, one that reuses and recycles materials, minimizing waste and ensuring resources continue to flow. It's a strategy used in both nature and advanced industrial systems. Agrivoltaics, combining solar panels with farming. Anaerobic digestion, turning organic waste into energy. Cold chain management, keeping produce fresh using efficient energy systems. Now, here's the challenge to think about. How can we design farms that create as little waste as possible? And more importantly, how do these innovations connect to your everyday life? Maybe it's what powers your food delivery, or how grocery stores manage waste. The idea of agrivoltaics is a smart solution where food and energy are harvested from the same land. Imagine growing crops like lettuce or spinach directly under solar panels. These crops benefit from the shade, which reduces water loss, while the panels stay cooler and produce electricity more efficiently. Studies show that this dual-use system can actually increase combined productivity, achieving both solar power and crop yield at around 80% efficiency each, resulting in over 160% land use efficiency in total. Here's the key takeaway. Agrivoltaics enables us to optimize limited land for multiple purposes, particularly in regions where land is scarce or prone to drought. Think about this question. Can we grow food and produce clean energy without needing more land? That's what agrivoltaics helps us do. Agrivoltaics is when we grow crops underneath solar panels. It's smart because it allows us to use the same land to grow food and generate electricity simultaneously. The shade from the panels keeps crops like lettuce and kale cooler, helping them use less water. The plants give off moisture that actually cools the panels, making them more efficient. And keeping plants on the ground helps prevent erosion and protects the soil. So it's a win-win. Healthier crops, better solar performance, and land that stays productive. Now, let's look at where this system works best. Agrivoltaics thrives in dry or low productivity areas, such as deserts or drought-prone regions. It supports crops such as leafy greens and strawberries, helping to resolve the conflict between food and energy production on land. However, to make it work, we need innovative design, local training, and policy support, such as pilot programs or subsidies. In the past, using land for solar panels usually meant taking farmland out of food production. This creates a conflict, especially in areas where land is scarce or already under stress due to drought and climate change. Thus, agrivoltaics presents a novel approach. Instead of choosing between food and energy, we can design systems that provide both. This creates a shift in how we can utilize land in agrivoltaics, turning land into a shared resource, not something we have to divide up or sacrifice. By challenging the way we've traditionally planned land use, agrivoltaics has shown us what is possible when we integrate, rather than separate, our food and energy systems. On the other hand, let's talk about turning waste into energy. Imagine if we could transform materials like cow manure, food scraps, or crop leftovers into clean fuel and fertilizer. That's exactly what anaerobic digesters do. Anaerobic digesters are like giant stomachs. They break down food scraps, manure, and crop waste without oxygen. This process creates two valuable outputs: biogas, primarily methane, which can power homes or be converted into electricity, and digestate, a slurry that works like a natural fertilizer for crops. We go through 4 stages. 1. Hydrolysis, where big molecules such as carbohydrates, proteins, and fats break into smaller ones. 2. Acidogenesis, where microbes turn those smaller molecules into acids. 3. Acidogenesis, where acids get turned into acetate and gases. 4. Methanogenesis, where methane, an energy-rich fuel, is formed. Thermodynamically, these are exergonic reactions, meaning they release energy, which we capture from methane. Bonus: the leftover digestate contains nitrogen, phosphorus, and organic matter, which helps fertilize fields and close the nutrient loop without the use of synthetic chemicals. Let's talk about anaerobic digesters. Imagine if we could transform materials like cow manure, food scraps, or crop leftovers into clean fuel and fertilizer. That's exactly what these systems do. So here's how it works. Inside a big, sealed tank with no oxygen, bacteria go to work breaking down the waste. But they don't just do it randomly. They go through 4 crucial steps, much like a relay race, where each group of bacteria passes the baton to the next. It starts with hydrolysis. At this stage, the bacteria break down large molecules, such as carbohydrates, proteins, and fats, into smaller pieces. These smaller pieces are easier to digest. And just like in cooking, this first step can take the longest if you're starting with really tough materials, such as straw or corn stalks. Next up is acidogenesis. Now that everything's been chopped down, another group of bacteria comes in and ferments it. They turn it into these special compounds called volatile fatty acids, VFAs for short, along with things like hydrogen, ammonia, and carbon dioxide. It's kind of like how old milk turns sour. This is a natural acid-forming process. Then we get to acidogenesis. Those VFAs are further converted into acetic acid, which is basically vinegar, plus more hydrogen and carbon dioxide. These are the perfect ingredients for the last group of microbes. The final step is methanogenesis. Here, a very special type of microorganism, called methanogens, takes those ingredients and makes methane gas. That's the good stuff. Methane is a fuel that can be burned, converted into electricity, or even cleaned and piped into the gas grid. So what do we get at the end? 2 major outputs: biogas and digestate. Biogas is mostly methane, and it can be used just like natural gas, but it's renewable. The second product is digestate. It's the leftover liquid in solids, and it's actually full of nutrients like nitrogen, phosphorus, and potassium. Now here's the cool part. Farmers can use digestate as a fertilizer once it has been treated, and also as a soil conditioner. It improves texture, supports soil microbes, and reduces the need for synthetic fertilizers. So we are closing the nutrient loop. Waste goes in, energy and nutrients come out, and the cycle continues. And beyond the science, let's talk about why this matters. Anaerobic digesters help with 3 major things. First, they tackle waste management. Instead of food rotting in a landfill and leaking methane into the air, we capture it. Second, they provide energy security. In rural areas, farms can generate their own fuel rather than purchasing it. And third, they help fight climate change by reducing greenhouse gas emissions. So just imagine, one system, powered by bacteria, can turn trash into treasure, fuel to power our homes, and nutrients to nourish our soil. That's anaerobic digestion, and it's one of the smartest ways to make farming more sustainable. And now that we understand what digesters produce and why they matter, let's take this a step further with an optional extended learning activity. This is our Digester Spotlight, where students will investigate a real-world anaerobic digester program and connect it back to the science we just talked about. In this group analysis activity, students will choose an actual digester, local, national, or even international. It could be a dairy farm digester in California, a municipal food waste digester in New York, or a community biogas system in India. The goal is to trace the full system. What goes in? What happens inside? What comes out? Students will identify the inputs, things like manure, food scraps, crop residues. They'll examine the processes, anaerobic decomposition, temperature control, microbial activity, and biogas capture. And they'll map out the outputs: methane rich biogas, liquid digestate, solid digestate, and how each one is used. Then comes the comparison piece. Students will contrast their chosen digester with landfill composting or traditional waste disposal. How does capturing methane differ from letting it leak out? Which system returns more nutrients to the soil? What are the environmental trade offs? These questions help students connect real engineering systems to climate, energy, and soil health. This activity brings the science to life. Instead of just learning about digesters, students explore how they operate in the real world, how communities design them, how farmers benefit from them, and how they reshape the way we handle organic waste. It's a chance for students to see sustainability in action through the lens of real technology, real places, and real impact. Now, how do we keep food fresh using less energy? Without cooling, food like milk and fruit can spoil quickly. Cold chain innovations help keep food fresh longer and save energy, which reduces waste and protects the environment. One example is solar milk chillers. They're great for places without reliable electricity, but can be expensive and need sunlight and maintenance. What ideas can you think of to solve those challenges? Let's pause a bit to discuss. Another tool is IoT temperature sensors. They warn us if the food gets too warm. Can you spot any problems with relying on these sensors? And how could we solve them? We also have phase change packs, like big ice packs that melt at 4 degrees Celsius to keep food cool during transport. They help avoid using diesel generators and stop food from spoiling. How long do you think warm milk stays safe without cooling? These packs help it last much longer. Please take some time reviewing this information and think about some questions, such as why does food spoil faster in some regions than others? How might cold chain improvements shift nutrition and food access in developing regions? Who should invest in these technologies? Governments, private companies, or communities? To bring all of this together, let's move into an optional activity corner where you get to step into the role of designer and problem solver. We've just explored different cold chain tools: solar milk chillers, IoT sensors, and phase change packs, and the big questions around access, cost, and who should invest. Now, you'll take those ideas and build your own solution. In this activity, your challenge is to design a low-cost, low-energy cold storage unit for a small rural farming cooperative in a region without stable electricity. Imagine a group of farmers who grow perishable crops but don't have reliable refrigeration. Your job is to help them protect their harvest. First, decide: what crops will your unit store? Are you focusing on tomatoes and leafy greens, milk and yogurt, root vegetables? Each one has different temperature needs and spoilage risks. Next, identify the optimal temperature range for those foods. Is it just above freezing, 4 to 7 degrees Celsius like a refrigerator? Or slightly higher for certain fruits and vegetables? Your design should match the biology of the crops you're trying to protect. Then, choose your cooling method. Will you use solar panels to power a small compressor or fan? Phase change materials, PCMs, that absorb heat as they melt? Reflective insulation to keep out sunlight? Passive earth cooling by partially burying the unit or using an underground chamber? You can even combine methods, but remember, it has to work in a place with unreliable electricity. You'll also need a way to monitor internal temperature. Will you use a simple analog thermometer, a low-cost digital sensor, or a basic IoT device that sends alerts when it gets too warm? Think about what is realistic and robust in a rural setting. Finally, estimate how much it will cost to build and maintain. What materials will you use? How often will parts need to be replaced? Who will pay for repairs? Try to balance affordability with durability so that the cooperative can keep using this system for many seasons. The goal of this activity is to think like both an engineer and a community partner, designing a cold storage unit that is not only technically clever, but also practical, affordable, and fair. By the end, you'll see how thoughtful cold chain innovations can directly shape food security, nutrition, and climate resilience on the ground. To wrap up, here are some review questions to answer. 1. What is agrivoltaics, and how does it let farms produce food and energy at the same time? 2. How do anaerobic digesters turn farm waste into energy and fertilizer? 3. What are cold chain innovations, and how do they help keep food fresh with less energy? Please take some time to review and answer these questions. Some possible answers to the questions would be: 1. Agrivoltaics combines solar panels and crops on the same land. The panels provide shade, and both food and energy are produced. 2. They break down manure and food waste into biogas for energy and digestate, which would be used as fertilizer. 3. Cold chain innovations are technologies similar to solar chillers and smart sensors that keep food cold without needing a lot of electricity, reducing food spoilage and energy use. As we wrap up Module 8, let's ground ourselves in the key ideas that tie everything together. First, energy shapes every bite. Every step of farming, from pumping water to powering greenhouses to transporting food, depends heavily on diesel and electricity. That energy has costs, financial and environmental. But when farmers shift to renewables like solar or biogas, they can dramatically cut both expenses and emissions. Cleaner energy means more resilient food systems. Second, do more with less. Modern tools like smart irrigation, tuned LED lighting, climate-controlled greenhouses, drones, and robotics help farmers grow more food using fewer resources. That means saving water, reducing energy waste, and cutting down on chemical inputs. It's all about precision, giving crops exactly what they need, exactly when they need it. And finally, design for dual harvests. Innovations like agrivoltaics and anaerobic digesters let farmers get multiple benefits from the same land or waste stream. One field can grow crops and generate solar power. One pile of manure or food waste can produce fuel and soil nutrients. These systems turn farms into engines of renewable energy and circular sustainability. Together, these ideas show how sustainable agriculture isn't just about growing food. It's about redesigning systems to be smarter, cleaner, and far more efficient. Take a look at this mind map. Notice how it forms a loop. This reflects a central theme. Designed agricultural systems are designed to recirculate resources rather than discard them, creating a more sustainable and regenerative approach. A central theme has been the development of farming systems that reuse resources rather than discard them. Closing the loop means turning waste into input, energy from manure, water from condensation, food from what was once discarded. It's a systems thinking approach that aims to maximize efficiency and minimize impact. We are almost done with this module. Let's wrap up with some reflection. Think back on what we've covered. Which technology or idea stood out to you as the most innovative? If you could lead or support a project in sustainable agriculture, what would it focus on, and what challenges might come with it? Also, consider this. What role do you see yourself playing, in your career or even right now, in shaping more sustainable food and energy systems? These aren't just concepts, they're real technologies already changing how we farm and manage resources. Whether you're interested in engineering, policy, science, or design, there's a place for your skills. So take a moment. Reflect on where your interests meet real-world impact. This is your opportunity to help shape the future. The key message here is, tackling today's agricultural challenges, like climate change, energy use, and resource efficiency, takes a wide range of skills. There are 4 major fields you could explore. Engineering, like renewable energy engineers, who design clean energy systems for farms. Tech and robotics, roles like precision agriculture analysts utilize drones and data to enhance farming efficiency. Policy and economics, policy analysts help shape agricultural laws and programs. Climate justice, community resilience coordinators support vulnerable communities that face climate-related impacts. No matter your interest, tech, design, science, or advocacy, there's a meaningful career where you can make a difference. Think about where your passion fits in. All right, everyone, these are your 2 hands-on activities for this module. In HOAA, you'll spend time with Dr. Elias Gutierrez's team and see how farms use drones and sensors to spot plant stress. Then back in class, you'll work with a small dataset consisting of things like NDVI, canopy cover, leaf temperature, and soil moisture. Then make a couple quick graphs and decide which crop plots look drought-stressed. You'll finish by recommending one action a farm manager should take. In HOAB, you'll be the consulting team on a farm or agri-tech field trip. You'll use a checklist to audit how the site handles energy, water, and waste, talk to staff, and document what you observe. Then you'll come back and propose 3 realistic improvements to help the site move closer to net zero. So it's basically diagnose stress with sensor data or audit a whole system like sustainability consultants.